Okay, welcome to our series of lectures on differential operators, fields and differential operators. We have already studied divergence, curl, gradient and curl, and also formulas related to the divergence and curl which was written here in the blackboard. Today we are going to learn something about Green's theorem, and we'll do some problems related to the divergence and the gradient and curl. So what is the Green's theorem? We will start for today is Green's We have studied that the operation of del operator on a vector field results in a scalar field which is called the flux of the field A per unit volume, and this is called a divergence. Then we have studied what gradient. When del operator operates on a scalar field, this phi is a scalar field. This is called the gradient, and this results in a vector, and the direction of the vector is along the increasing magnitude of phi. And then we have studied about curl. Curl is applied only on the field which is rotating field. This gives you that is, if A is a field which is rotating, that the curl of A means the line integral of this, the A, what the whole circular path per unit area. So when it is this circular path encloses an area of some surface area. So this we have already done, and now today we will do Green's theorem. So Green's theorem is, suppose we have two fields and we take the gradient of one field and multiply the gradient of that field with another field. Let U and V are two scalar fields that U and V are two scalar fields. The gradient of V, scalar field V, written as del V, will be a vector field, because we know that the gradient of a scalar field results in a vector field. So the gradient of V will be a vector field obviously. The multiplication of another scalar field U with the gradient of V will also be a vector. Obviously, the multiplication of a scalar field of a scalar field U with gradient of V will be a vector field. Because we know that a scalar multiplied by a vector results in a vector. So this is, now suppose this a u multiplied by gradient of v. So this is the gradient of v multiplied by u scalar field. This results in a vector field, say A. Now take the divergence of A, this vector field, and see what the results comes out to be. So the divergence of A will be divergence of u this is the divergence of A. The A is this quantity. So divergence of A means divergence of u. Now del is del by del x I plus del by j plus del by del z k, and this is u del v is del v by del x plus del v by del y plus del v by del z. So this will be u times del v by del x I plus u times del v by del y j plus u times del v by del z. Now, this del by del x will operate on this. So, this I dot I will be 1 and I dot j will be 0. So, this will operate only on this one. So, this means del by del x is operating on u times del v by del x plus. Now this will operate only on this value because here it is j, it is I, and this is the dot product here because you are taking, yes, this one, you are taking the divergence. So this I dot I will be 1, so this is there. I dot j will be 0, I dot k. Similarly, j dot I will be 0, j dot j, this factor remains. So it will be del by del y u del v by plus. Now similarly k dot k will remain, all other terms will be 0. So this is del by del z u del v by so this is the product of two functions. So this will be del u by del x operate, this will remain as it is, plus x u will remain as it is, and this will operate on this. So this will be del square v by del x square plus. Now this will operate on this, and then in the next term on. So this will be du by del y del v by del y plus u del square v by plus. Now this operate on this first and the plus operate on this. So it will be delta u by delta z delta v by plus u times delta square v by now we will rearrange. We will take this term, and this term in one bracket and the remaining in the another bracket. So it will be del u by del x del v by del x plus this term del u by del y del v by del y plus third term del u by del z del v by del z plus the remaining term, this one, and this one. So in all these u is common. You can take u as outside also. So it will be, if you take u outside the bracket, this will be del square v by plus del square v by square plus del square v by del z square. Now, okay. So this will be del u times del v, this bracket, and plus times this will be del square, this is del square, so it's del square. So we found out that divergence of A is this quantity. Now take the volume integral of this divergence. So I am writing this equation above here and remove this one. So this is divergence of A is equal to du dv del u del v plus u times del square v. So this is the divergence of the vector field A. Now take the volume integral of this divergence. Take the volume integral of the above equation. You can name this equation as 1 also. Equation say 1. Take the volume integral. So the volume integral is integrated over the volume. This is the volume. Okay, you take the V is a capital because we have taken as a field here. So for volume, take this V. Now from the divergence theorem, Gauss's divergence theorem, we know that the volume integral can be transformed into surface integral. Because A is a vector field and integrated over the divergence of A over the volume. This is the divergence of A over the volume. Can be written as flux of A over the volume over the surface. This is the flux. So from volume integral we are going to surface integral. This is called Gauss's divergence theorem. So using the Gauss divergence theorem, we can write this side into surface integral. So using the Gauss divergence theorem, the left hand side, transform left hand side of this equation says 2 into surface integral. Using Gauss's divergence theorem. Transform the left hand side of equation 2 the left hand side of equation 2 into surface integral to from volume equation from volume to surface integral from volume to surface integral. So this will be A dot where A is U times delta V. U was U times gradient of V, and this comes out to be on the left. So this will be remain everything here same, del U del V, gradient of U gradient of V plus U del square V D. So this side, the left hand side is changed to surface integral. So it is A ds flux of A, and the value of A is U del V. So now U and V are two arbitrary scalar fields. we can replace u by v or v by u. So if we replace u by v, the here it will be v, this will be u, this will be v, this will be u, this will be v, this will be u. So replace u by v. And this relation is called Green's first theorem. First that is the surface integral of this value u gradient of v is equal to, then the right hand side is distributed. Now replace u by v. U by v in equation 3. If you replace this, you will get v gradient of u surface the flux also. This will be v, this will be u, plus v del square u, take it, consider it as 4. Sure. Now subtract 4 from 3. 4 from 3. So subtract that is u del v minus v del u. This minus this is equal to, if you take subtraction, this term will cancel out because the same thing, del v del u del v del u cancel out. You will get u del square v minus v del square and this is the Green's second theorem. Okay, in the next class we will do some problems related to del operator. I am leaving today because that will take some more time. So in the next class, that will be on the next class.